Hello everyone. So today let's solve the problem new year and finding root. So this was asked on Codeforces. This one goodbye 2016. Yeah. So this was the last question I believe in the 2016. I believe. Yeah. I mean a last contest actually. I think so. Yeah. So this is fine. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Yeah. So this is rated around 2800. So this is going to be the difficult one. Yep. So this is fine. Yeah, you can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. So let's see what the question states here. Right. So we are given a perfect binary tree. Right. So we are given a perfect binary tree of height h greater than or equal to 2 and less than or equal to 7. Yeah. H greater than or equal to 2 and h less than or equal to 7. Yeah. So but only via queries. But only via queries. For any vertex x, we can ask its neighbors. For any vertex x, we can ask its neighbors. So using less than or equal to 16 queries, see, using less than or equal to 16 queries per test case, we must identify the root. What we need to do? We must identify the root. The unique root, nothing but the unique vertex with degree 2, right? So the unique vertex with, we have to identify root, nothing but unique vertex with a degree 2, right? Unique vertex with the degree 2. Yeah, just remember this one. Internal root of the perfect binary tree we have to find in simple terms. Yeah. So, so this is nothing but the interactive strategy for the hacked input and the output, right? The root index when found actually in simple terms. Yeah. So this is what the question states in simple terms. Let me read out the question loud. Just listen to this carefully. We are given a perfect binary tree of height h greater than or equal to 2 and less than or equal to 7, but only via queries, right? For any vertex x, we can ask its neighbors. For any vertex x, we can ask its neighbors. Using less than or equal to 16 queries per test case, we must identify the root. Yeah. So the unique vertex with a degree 2, the unique vertex with a degree 2, nothing but the root I said, right? We have to identify the root. So it is nothing but the unique vertex with a degree 2. So internal root of the perfect binary tree. All we have to find is internal root of the this one perfect binary tree. Yep. So this is the question, man. So I'll just delete this one. So let me come to the input output part here. Right. See here, we have been given h3, right? So h we have been given 3 here in this case. So input we have been given only 1. H we have been given 3. Yeah. So n we can consider just 1 and h we have been given 3 here. And we have 7 nodes here. You can just see by looking at it, we can tell here. It starts from here. 1, 2, 3, 4, 5. This one, 6 we don't have, but 7. Yeah, totally from 1 to 7, we have 7 nodes actually. Yeah. So by looking at it, you can say this is fine, man. So the output that we need to get here is this one. We have to find the root. Root, right? Root, nothing but the unique vertex with the degree 2 actually. Yeah, the internal root of the perfect binary tree. So here in this case, we have to get the output this one. 5, 1, 5, 6, and 5. We can have the multiple outputs, I believe, for this one. Yeah, so this is fine, man. So this is about the question and the input output part. Let's do one thing. Let's quickly discuss the approach followed by the complexities part, and then let's write the code. Yeah, as usual, let's discuss the approach first, right? So first, let's go with the idea actually, right? So we have been given. So one second, just give me a second here. Let me consider the same first example, man, for the this one approach. It will be easier to understand for us, right? So h height we have been given 3 here. Let's consider the same. N we have been given only 1 here. H we have been given 3. Yeah. So yep. H we have been given 3 and we have 7 nodes here. So we have already discussed here. We have 7 nodes here, right? So let's discuss this one step by step. Let's hop into the approach part. So before hopping into the approach part, all I want to say is all we have to find is the root, right? So we can just go with a DFS, or let's do one thing. Let's go with a bidirectional, this one DFS. This will be easier for us to solve the problem actually. So let's go with a bidirectional DFS to solve this particular problem. Yeah. In short or in simple terms, we can just call this one DFS. Yeah. Or the bidirectional DFS. Yes. So let's this one. Let's discuss let's discuss this one step by step. First, what we'll be doing, we will be starting at the node, nothing but the when p equals 1. We'll be starting at the node when p equals 1. Next, we will query its neighbors. We will query its neighbors. We'll query its neighbors, right? So this is fine. What we'll do, we'll start at the node p equals 1. We'll query its neighbors. If any queried vertex has the degree 2, then it's the root. If any queried vertex has the root, then uh, has the degree 2, then it's the root. If any queried vertex has the degree 2, then it's the root, and we will report it. And it's the root and we'll report it. So this is the first thing, right? Otherwise, if the vertex doesn't, if any of the vertex doesn't have the this one degree 2, then we will pick an unexplored branch, yeah, and greedily walk to the middle of the path, and greedily walk into the middle of the path, right? What we'll do, and greedily walk to the middle of the path, right? Greedily walk to the middle of the path, right? So between two fringe branches, right? The solution builds two partial paths here. One is left and another one is right from the chosen pivot, right? So we know this one. What we are doing first, we are starting at the node p equals 1. Then we are querying its neighbors. If the queried vertex has degree 2, then we have successfully found the root, right? That's the criteria in the question they have given actually. Then we have found the root, then we will report it. This is one thing. Otherwise, if any queried this one, if any vertex doesn't have the degree 2, then we will pick an unexplored branch and greedily walk to the middle of the path between two fringe branches. Yeah. So the solution builds two partial paths here. One is left, another one is right from the chosen pivot using DFS. So we will be making use of the DFS as I've said. Yeah. So using DFS, that only expands already queued nodes first to consider the queries here in this case. Yeah. So this is fine. So the third point, let's move on with the third point, right? So now what we will do, we'll combine two walk paths into the single path. What we'll do here, we'll combine two walk paths here, two walk paths into the single path actually. Single path. We can just call this one as G actually. Yeah. So we will be combining the two walk paths into the single path G from the leaf-like node through P. From the leaf-like node through P to the opposite branch. Then choose the middle node mid. Then we will be choosing the middle node mid of G as the new pivot P. Yeah. Then choose the middle node mid of the G as the new pivot P. This advances the depth by about half the path length. Yeah, this advances the depth by half the path length. Then we'll iterate. So this is going to be the third step. Then finally, let's move on with the fourth step here. So when the remaining depth to the root is small, when the remaining depth to the root is small in the sense if it is less than or equal to 3. I'm speaking of less than or equal to 3. When the remaining depth of the root is small or less than or equal to 3, the whatever the algorithm that we perform, this one DFS actually, performs a bounded BFS expansion. So we'll be making use of the BFS as well along with the DFS, right? So the algorithm performs a bounded BFS expansion and stops as soon as the node of degree 2 is discovered. So we'll stop as as soon as the node of degree 2 is found. Node of degree 2 is found. So we will be going with the BFS expansion as well. Yeah. So basically algorithm performs a bounded BFS expansion here. So as soon as then is this one node of degree 2 is this one discovered actually. Yeah. 1 second. I'm getting a call. So here, when the remaining depth of the root is small or less than or equal to 3, the algorithm, what it does, it performs a bounded BFS expansion and stops as soon as the node of degree 2 is discovered, right? So basically, whatever the code we write, it throws found exception immediately when the degree 2 is seen and it prints the root in simple terms, yeah? So this is going to be the idea. Right? So this is what we will be doing and this is the approach that we'll be going with actually. In simple terms, we'll be going with a bidirectional DFS along with the help of the BFS, right? So mainly we'll be going with a bidirectional DFS to solve this particular problem. So this is going to be the idea. Also, we'll be making use of the greedy approach. Yeah. So this is fine, I believe. Yep. So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities accordingly with the approach that we discussed, right? Yeah. Now, so what's going to be the time complexity here? The time complexity would be big O of 2 to the power of h here. So why it is big O of 2 to the power of h actually? In the worst case, see, uh, here in this case, in the worst case, it would be big of 2 to the power of h. We can query at most big of number of nodes, right? Number of nodes accordingly with the input, but it is bounded by the problem limits. Yeah, and 16 interactive queries they have mentioned. So practically bounded and small since h has to be less than or equal to 7, the constraints part I'm speaking of. Yeah, so overall time complexity you can just consider as big of 2 to the power of h. Or, yeah, so what will be the space complexity? Space complexity would be 2 to the power of big of 2 to the power of h as well. So we'll be making use of the adjacency cache as well as the path list here, right? So again, it is small since h is less than or equal to 7. Yeah, the time complexity and the space complexity for the code that we'll be writing in the future would be big of 2 to the power of h actually. Yeah, this is fine, I believe. So yeah, as we are completely familiar with the approach and the complexities part, now we are good to write the code. Let's start writing the code. Yeah, first, let's do one thing. We'll be making use of the fast input and the output along with the different utilities. Let's import this one, input output package as well as the utility package. So now, as I've said, let's do one thing. So I'll just import here input output package as well as let me import here utility package as well. Yeah, this is fine, man. Now let's go with the this one class actually. I'll just name this main. You can just go with any class name that's relevant to the question. Yep. So this is fine. Now let's go with the maximum nodes for h up to 7. Yeah. So up to 7, I'll just make use of this one left shift operator here. One left shift operator 7 I can just make use of, right? Minus 1 is equivalent to the 127. Let's just add a little bit padding. I'll just go with 1 left shift 7 plus 5. So here 1 left shift 7 minus 1 equals value 127. Yeah, so let's just add little bit of padding here. For just I'll just go with a one left shift 7 plus 5 for the safety side. So I'll just go with here static final int n equals. So I'll just keep this one capital N. Yeah, so this one shift 7. Let me go with plus 5 for the safer side. So this is fine. Now let's go with the current test tree height. So this one I'll just name this one static int. Yeah, so this is fine. Yep, this is nothing but the tree height man in simple terms. Now let's go with the adjacency info cache. Yeah, so I'll just make use of array list here. So this one will be list of integer. This is fine. Let me, this is the array, right? This one variable b new is not showing. Oh, I haven't typed the list here. So this is fine. Let me complete the syntax here. So this is fine, I believe. I think we have to go with the size n, right? So this is fine. Sorry. Yeah, this is fine, man. Now, let's do one thing. So let's make use of the this one, a fast reader as well as the print writer. So I'll just be going with a fast reader, or you can just make use of the buffered reader as well. I'll just go with a custom input here, fast reader, right? So let me go with static. So let me leave space here. So this one will be static list of integer. So this is fine. Let me go with the get here. So this one will be x. Also, let me go with the fast reader variable input, nothing but n. Also, let me make use of the print writer here. Let me go with a variable out here. So let me make use of throws input output exception as well, or let me go with the throws found exception. Yeah. So here, let's just go with a found exception. So this is fine. Yep. Now within this method, let's start writing within this method, man. Yeah. So if we haven't asked about x yet, and nothing but if the list is empty, then we have to query or read it, right? So this is very simple. So let me go with the simple if condition here. If v of x, me make use of is empty here. This is fine. Then within the if condition, let's go with the interactive query, right? So this one, we have to display this one, I believe, question mark along with the, yeah, this is fine, man. Just give here out dot println along with it. Let's display question mark and leave the space here. So this is fine. Also, let's append the X here. Yep, we have to append the X. This is fine. Now, after doing this, we have to flush. Let me make use of the out.flush. So this is fine. Next, we have to read the number of neighbors returned, right? So this one will be int m equals uh, next int. So this is fine. Yeah. So next, let's go with the iteration part. So this one will be for I equals 0, I less than m. So this will be I plus plus. Yep. So this is fine, man. Yeah. Now let's read the neighbor index as well as let's store the neighbor in cache. Let's do these two things. First, let's read the neighbor index. So this one will be p, variable p. Let me assign this one to the again next int. Yep. So this is fine. Finally, let's store the neighbor in cache. Nothing but v of x dot. So let's add the p to v of x actually here in simple terms. This is fine. So let me come out of this one entirely, the for loop I'm speaking of. Now, if node X has exactly two neighbors, then it is the root according to the criteria of the question, right? For h greater than or equal to 2, we are speaking of. If node X has exactly two roots, so this is the first step that we discussed in the approach. If node X has exactly two neighbors, it is the root, right? So this one, if I can just write in this way, if v of x here dot size uh, size if it is exactly equivalent to the 2, then let me go with throw new. Let me make use of the found exception here. Yeah, so we have to pass x. We have successfully found the root. This itself is the root, right? Then we have to return the cached neighbors, right? So I'll just come out of this one. So this one will be return v of x. This problem is completely based on this one graph with the trees actually. You can just say this one graph along with the trees. Right, so this is fine. Let me come out of this one entirely now. So now let's move on with the this one second step actually. Otherwise, this one we discuss something, right? So I said you one thing while explaining the approach that we'll be going with uh, BFS, bounded BFS, right? So let's go with the helper node class for the BFS like queue operation, right? So let's do that first. So I'll just go with here static. So this one will be class node. So within let me make this one capital M. So this is fine. So within the node, I need two things. One is X and another one is, yeah, DIS. So this is fine. Let's move on with the constructor part here. So this one will be node of what are the two things that we considered? X and DIS keyword, right? So this is fine. So let's initialize this one very quickly. This dot X equals X. Also, this dot DIS equals, let me assign this one to the DIS. So this is fine, man. Let me come out of this one entirely now. So now we have to go with a custom exception that is used to immediately return the found root throughout recursion or the logic. Yeah. So again, we'll be going with a found exception. Don't get confused here. So I'll just go with static here class. So let me go with a found exception here. So let me give extends exception. Yeah. So this is fine. So initially, let me go with the answer. So this is fine. Uh, Let me go with the found exception of int a. Yep. So let me assign answer to the a. Let me assign answer to the. So let me come out of this one entirely as well. Now, as I've said, we'll be making use of the DFS. DFS, what it does here, it extends the path G, right? Accordingly with the this one, what we have discussed in the approach actually. DFS just extends the path G starting from X while preferring already known nodes first. Yeah, right. So that's what we will be doing here. So let's do one thing. Let me write this one. This method actually static void DFS actually within the DFS I need X. I need FA as well. So what does this FA variable do? FA is nothing but the parent to avoid going back, right? It adds the visited nodes to the list G that we have considered. Yep. So let me consider G as well. I haven't considered that one yet actually. So let me go with the integer, stop integer G, as well as let me go with a fast reader. So this one has to be in. So let me change this one to the capital F one. So this one has to be capital F. Somewhere I have given small f, I believe. So this one, let me change this one to the capital F as well. Yep, so this is fine. Fast reader, nothing but the variable in, and also print writer. This one, let me consider out actually. This is fine. So I'll just go with throws found exception. This part, yeah. So this is fine. So within this method, DFS method, the first part is we have to add the current node to the path. So this one, I'll just go with g dot add of x actually. Simple, simple. Now let's go with the first loop, man. So we have to try to continue along neighbors that are already known, right? So initially cache, we shouldn't keep the cache empty, right? So cache not empty here. First, let's try to continue along its neighbors that are already known in simple terms. So let's go with a for loop here. So this one will be in I. Let me go with a get. Let me pass x in as well as the out. So this is fine, man. So within the for loop, let me go with a simple if condition. If neighbor not equal to the parent, and if we have already queried it, then we have to continue the DFS there. Also, we have to return once extended in that particular direction, means we have to get out from there, or we have to terminate or exit from there, right? So let me write the simple if condition. If I not equal to FA, and along with that not of V of I actually, let me make use of the is empty operation here. Is empty. Then what we need to do here, let's recurse here DFS of, have to pass I x the parameters, this one G as well, in and out, in for the fast reader and out for the print writer. Yep. So this is fine. Finally, we have to return. Let me give return here, right? We have to exit, right? So let me make use of the return statement. Let me come out of this one entirely. Now, let's go with the second loop. We are done with the first loop part. So if no already neighbor to continue, then we have to expand to any neighbor, right? So I'll just go with one more for loop here. So this one will be for int I of. So let me make use of the get again here. What are the parameters? X input as well as the output fast reader and the print writer. So within the for loop, let me write the similar thing. If I not equal to FA, then let's recurse again DFS of I comma X, G fast reader variable and the print writer variable in and out. Finally, let's return from here as well. Means we have to exit from here. So this is fine. Let's continue. Now let's continue where we have left. So let's write the helper method solve where we perform the main logic here, the core logic. Let's return in the solve method. Let's write that one in the solve method. Sorry. Let's make use of the solve method where we write the core logic or the main logic, and then we can just make use of it within the this one main method. Main method. Yeah. So I'll do one thing. Let me write here static void. Let me go with a solve here. So I'll just go with a fast reader variable here input and print writer variable out. This is fine. These two are enough. So let me go with throws found exception. Yep. So within this method, helper method solve actually, let's do one thing. First, let's read the height, nothing but the h for the particular test. So I'll just go with h equals in dot. Let me make use of the next int. Yeah, this is fine. Now let's move on with the for loop here. This one will be int I equals 1, I less than 1, left shift h here. So let me increment the I. So this is fine. So I'll just go with v of I dot clear, v of I dot clear, right? So this is fine, man. Yep. Now let's do one thing. Let's go with a this one. Let's initialize certain things. Yeah. Let's go with the variables p, x, y, and dep. So what is p here? current pivot node, which starts at the 1. We know this one from the approach. We have discussed this one. Current pivot node start at 1 actually initially, right? X and Y. What are the X and Y variables here? X and Y will be so X will be X and Y both actually. They are the immediate neighbors around the pivot, right? Basically, they are used to avoid revisiting the same edges. Yeah, this is fine, I believe. Now we know P, X, and Y. So we will be making use of variable DEP. DEP is nothing but the current known distance, right? In terms of the middlemost, right? So we will be setting this one to the -1 initially because it means not yet set. We haven't set yet, right? The current known distance we don't know. We haven't current set that one yet. So these are the variables that we'll be initializing. So I'll just be going with int p equals 1, x equals 0, y equals 0, as well as dp equals -1. Yep. Now we have the idea. So let's move on with the this one. What do we call? While loop here. While of Boolean value. So this is fine. So within the while loop, let's get the neighbors of the pivot P. So we make query if unknown, right? So I'll just go with the list. So this is of the type integer. This is fine. Let me go with a variable G. So this will be new array list. So let me go with this one. What do we call? Get of P input. So this one will be, yeah, this is fine. Now let's remove previously used neighbors, nothing but x comma y from this particular neighbor list. So we pick fresh, right? So we pick fresh branches. Yeah, we are removing the previously used neighbors, nothing but x comma y from this particular neighbor list. So we pick fresh branches. Yeah, so how can we write that one in the form of code? So let's write two if conditions actually. So I can just write it on this way. If x not equal to 0, let me go with g dot remove here. So this one will be integer dot value. So this one value of let me pass x here. So this is fine. Let me do the same thing for the y as well. So let me copy this one entirely. Yeah. So let me paste this one over here. Yeah. If y not equal to 0, g dot remove. So this one integer value of y. So this is fine. I'll just go with the y here. Yeah. Instead of x, let me change this one to y. The only change actually. Here y and here y. This is fine. Yep. Now let's move on with the further things. So if we have advanced this one depth, nothing but the distance, such that the remaining depth to go is exactly 0, right? The remaining depth is go the remaining depth to go is exactly 0, then the unique neighbor is the root itself. Yep. So we can just write it in this way. Let's consider one more if condition for this. So I hope this works, man. So many ifs actually. So this is fine. F plus 1, if it is equivalent to the h, then I'll just give here throw new. Let me make use of the found exception here. Let's pass g dot get. What do we need to get here? So initially 0, right? So this one has to be 0. Yep. As I've said, if we have advanced DEP such that remaining depth to go to is exactly 0, right? So that is the reason I'm passing 0 here. This is fine. Now let's move on with the further things. When we are very close to the root, meaning remaining height is small, we do the bounded BFS from the current branch. We do the bounded BFS from the current branch, and we will stop when found, right? So let's move on with the BFS. Let's perform the BFS here, right? So I'll just go with one more if condition here. DEP not equal to -1. It shouldn't be equal to -1, and h minus DEP here. If it is less than or equal to 3, then what we will do, let me go with the queue here. Let me go with the queue. I'll just go with the node q equals this one new. Let me go with linked list. New linked list. So this is fine. Yep. Now let's go with q dot add of new node. This one is fine. G dot get. So this is fine. 0. So I'll just go with h minus dp minus 1. So this is fine. Yeah. Now let's go with a while loop. while of not of q dot is empty. So this is fine. Standardized BFS loop actually. Yep. So this is fine, man. So this is the standardized BFS loop, right? So first, let me go with the top. Let me assign this one to q dot poll. Yeah, we are just going with a pure BFS here. If the queue becomes empty and we are at the distance 0 and that particular node itself is the root, we know this one, right? From the criteria actually. If queue becomes empty, if queue completely becomes empty and we are at the distance 0, right? And that particular node or this node is considered as the root actually. I can write it this one by making use of if condition. So if q dot is empty, queue itself, sorry, if queue becomes empty and we are at distance 0, right? I'll just go with top dot dis variable we have made use of for the distance. If it is equivalent to the 0, then this node itself is the particular root, right? So I'll just go with throw new found exception top dot x. So this is fine. Now let's move on with the for loop here. This one for mm, I mm, get of what are the things that we need to pass here? Top dot x here. Uh, this one pass data variable as well as the print data variable. So within the for loop, let's expand only to not yet queried nodes, and while we still have remaining what? While we still have remaining distance. Yeah. So this one I can just write it in this way. If v of I, let's make use of the this one is empty operation here is empty, and let me go with top dot distance, this one if it is greater than 0, then let me go with q dot add of here new node. Let me pass I along with the I. Let me go with top dot this one distance minus 1. Yep. So this is fine. So let me come out of this one entirely, man. Let me come out of this one entirely, right? So let's do one thing, or mm, we have to come out of this one entirely, right? Of the three, I think. If as well as the so this one. Yep. I'll just come out of this one entirely. Now let's build the path G. So we have to collect the nodes from one branch that is reversed. Also, we have to collect the pivot P, then the opposite branch as well. In simple terms, let's build the path G here, right? So I'll just go with list here. This one, let me go with integer G equals new array list. So let me complete the syntax here. So this is fine. Yep. So if we have X, basically, if we have X defined or there are more than one neighbor, then we have to start the DFS from X, right? So I'll just go with the if condition again. If X not equal to 0 or size of the G, if it is greater than 1, if it is greater than 1, then let's recurse. I'll just go with the DFS here x not equal to 0. Uh, so let me go with here x. Let me go with g dot get here. So this one of 1, this is fair. Let me go with p. Also, let me go with g. Let me go with uh, first reader variable as well as the print writer variable in and out, input and output basically. So now after recursing, we have to reverse. So this side will be before pivot. So I'll just make use of the collections man here. So collections dot reverse we can make use of, right? So what we need to reverse actually G. So let me pass G here. This is fine. So let me come out of this one entirely now. So let's add the pivot in the middle accordingly with the approach that we discussed. So this one will be G dot add of V. Simple. Now, again, let's recurse. So we have to extend from the other side as well. So I'll just go with a DFS here. So this one will be G dot get. So we are making use of the bidirectional DFS, right? So we will be making use of the DFS everywhere. Yeah. So this is fine most of the time. So you'll see DFS everywhere, right? So this is fine. G dot get. So this one of 0 along with P G in as well as the out. Yep. So we are just extending from the other side as well. Now let's move on with the further steps, man. So we have to choose the middle node of the build path G as the new pivot, right? So let's calculate the mid. So I'll just go with mid. We are almost at the end of the logic actually. Before writing the main method, we are almost at the end of the logic. So we have to calculate the mid. We have to choose the middle node of the build path G as the new pivot. So this one will be mid equals G dot size divided by 2. So this is fine. So the next path is we have to go with a new pivot, meaning let's assign the P2 G dot get here of let me pass the mid variable. So this is fine. So also let's consider the left neighbor of the pivot. So this is used to avoid revisiting actually. So this one will be x equals G dot get here of mid minus 1. Yeah. So this is fine. Also y equals mm, G dot get of mid plus 1. So this is also fine. The final one here is we have to update the depth. So update the depth means approximate distance from the explode fringe to the pivot, right? So this one we can just give here depth equals this one mid plus 1. Yeah, so we are done with the logical part. So let me come out of this one entirely. Now let's go with the main method and let's call the solve method within the main method. So this one we have written within the solve method, right? So where did this solve method go? 1 second. We have performed the DFS. This one solve actually. Yep, so this is fine. uh let me go with the main here. Let me remove this one as well as um this is fine. Let's make use of the fast reader and the print writer. Fast reader. So let me call the variable in here new fast reader. So this is fine. So this is nothing but the fast input reader. And let's go with a print writer as well. So I'll just go with this one. Print writer out. So this one new print writer. So this one will be system.out, right? So this one will be system.out. Yeah. So this is for the fast output, right? Fast reader and the this one print writer. Yep. So let me go with int t equals and dot. So this one will be next int. Yeah, next int. Yep. So this one will be fine. So this is just the number of test cases, man. Yeah. So yeah, this fast reader. So this is going to be the custom fast reader. Custom this one input actually fast input. So we don't have to worry about that. So this is fine. Int equals so this is for the number of test cases. Let's move on with the further things. We have to initialize the adjacency list for all the nodes as well, right? So this one will be for int I equals 0, I less than n, as well as let me go with I plus plus here. So we have to let me give here b of I equals new array list. Complete the syntax here. This is fine. So I'll just go with while if while it is greater than 0, then within the while loop, let me go with a try catch here. So let me go with try. So let's call the solve method over here. So I'll just come here. Let me copy this one here. Uh, main this one. We have written the core logic or the main logic within the solve method itself, right? So let's call the solve method within the main method with the this one fast reader variable as well as the print writer variable in and out, right? So this is fine. Next part, let me go with catch. So let me pass found exception here. This one along with the e. This is fine. Yeah. So within this one, within the catch, let's print the found root in the required format. So this one is gonna be out.println. So this is fine. Yeah. So let me go with exclamation here. So this one is fine. E dot answer. So this is fine, man. Finally, let's go with the out.flush. Out.flush. So this is the thing. So we have to flush to ensure the output is delivered. Yep. So you can just close the output as well. Out.close also works here. So again, we have to go with the out.flush here. This is the final flush. This is going to be the final flush actually. Let me make use of the out.flush here. So this is fine. So let me come out of this one entirely. Now, the only thing that is left is we'll be going with the custom fast reader. You can just go with the buffer reader as well. So let me go with the custom fast reader as I'm going with the intense optimization. So let me go with this template itself. I'm used to it actually. So let me paste this one over here. Sorry, 1 second. So let me come here. Let me paste it over here. So this is purely related to the input output, man. This is purely related to the input actually. We are just going with the fast input. So you can just make use of any template of your choice, or you can just go with a just with a buffer reader as well. Yep. So it doesn't matter, right? I'm just going with this particular template, yeah, for the fast input. Yep. So this is it for the code actually. This is it for the code. I just copy pasted only this part actually. This is fine. So this is it for the code. So before checking the code with the different this one inputs or the examples, let me copy paste the signature starter template. So I'll just paste this one over here. So let me come to the problem F. So let me copy this one. The output that we need to get here is this one. Let's check what will be the output that we'll be getting actually. Error identifier expected. So yeah, we have to this one. We have missed the identifier. This is fine. Where is it actually? 45. We are going with what do we call actually x as well as the distance. So we have to go with the int distance actually. Just give me a second here. 1 second, man. So the class actually, yeah, 1 second. Yeah, where is this actually? Yeah, now let me give int here. So this is fine. Let me run this one. Yeah, just ignore this warning, man. We are getting 155, which is correct actually. Yep. So we can have the multiple outputs. That's not this thing. Uh, not to worry actually. So for this one, let's check. So yeah, this is fine. One double three, 1 2 3 we are getting right. So yeah, so for whatever code that we have written, for whatever the logic that we have written, right? So the output that we are getting is correct actually. So I hope this works actually. We have the multiple out. We can have the multiple outputs they have mentioned in the question. Let's see whether this works or not actually. Just go to the submission part and let me paste the code over here. Let me select F actually. This is question F, right? Yeah. New year and painting roads. Let me hit the submit button. I hope this works for all the test cases. Let's see. Let's wait for some time. So yeah, this is running on the test. You can clearly see here 33, 35. So this works actually. So for whatever the understanding of the question that I had, so accordingly with that this one, I went with the approach basically. And multiple outputs are allowed, they have said. So yep, this has to work in my opinion. Yeah, you can clearly see here, and the toast it is showing accepted, right? So the verdict that we got here is accepted, right? So whatever the code that we have written works absolutely correct for all the test cases. Here we have went purely with the bidirectional DFS, or we have went with the DFS. Also, for one part we have made use of the BFS actually, somewhere bounded BFS, right? Yep. Yeah, this part actually. Yep. So we have made use of the uh, a bit of BFS. We have made use of the BFS. It's okay. So we mainly we have went with a bidirectional DFS along with a BFS to solve this particular problem. Yeah. So we are gonna finish off this one. This part no, we still have this one two problems left actually. This is fine. We are done with the this particular problem, right? I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.